Welcome to Module 1 of this course on Material Science and Engineering Statics. In this first part of the course, we will focus on the fundamentals of material science. This includes understanding atomic and crystal structures, material bonding, and how these microscopic features influence the physical properties of materials. We will also classify different materials such as metals, polymers, ceramics, wood, rubber, and composites, while discussing theories like dislocation theory which explain the mechanical behavior of solids. Understanding material science is essential because every engineering system relies on materials to perform under loads, stresses, and environmental conditions. By knowing how materials are structured and how they behave, engineers can make informed decisions about which materials to use for specific applications. 1.1 Atomic structure and material bonding. At the most fundamental level, all materials are made up of atoms. The arrangement of electrons in atoms determines how they bond together to form solids. There are three main types of bonding that influence material properties. Ionic bonding, where atoms transfer electrons to achieve stability, often producing hard and brittle materials like ceramics. Covalent bonding, where atoms share electrons, producing strong, directional bonds as seen in materials like diamond and many polymers. Metallic bonding, where atoms share a sea of electrons, producing ductile and conductive materials like metals. Secondary bonding, such as van der Waals forces and hydrogen bonding, also influences material behavior, particularly in polymers and biological materials. 1.2 Crystal structures. In solids, atoms are arranged in specific patterns called crystal structures. The most common crystal structures include body-centered cubic (BCC), found in metals like iron at certain temperatures. Face-centered cubic (FCC), seen in materials like aluminum and copper. Hexagonal close-packed (HCP), present in metals such as magnesium and titanium. The type of crystal structure strongly influences material properties. For instance, FCC metals are usually more ductile, while HCP metals tend to be more brittle. 1.3 Physical properties of materials. Material properties can be divided into categories. Mechanical properties: strength, hardness, ductility, toughness. Thermal properties: heat capacity, conductivity, expansion. Electrical properties: conductivity, resistivity, dielectric strength. Magnetic properties: ferromagnetism, diamagnetism, paramagnetism. Optical properties: transparency, reflectivity, refractive index. These properties determine how materials perform in different applications. For example, copper is chosen for electrical wiring due to high conductivity, while polymers are used in insulation due to low conductivity. 1.4 Dislocation theory. Dislocations are imperfections in crystal structures. They explain why materials deform under stress. When a material is stressed, dislocations move through the crystal, allowing deformation to occur. The more easily dislocations move, the softer and more ductile the material is. Controlling dislocation movement, through processes like alloying and heat treatment, allows engineers to strengthen materials. 1.5 Classification of materials. Let us now classify the major groups of engineering materials. Metals. Ferrous metals contain iron, such as steel and cast iron. They are widely used in construction and manufacturing due to strength and versatility. Non-ferrous metals include aluminum, copper, zinc, and titanium. They are valued for properties such as corrosion resistance, lightness, and electrical conductivity. Polymers. Thermosetting polymers harden permanently when heated. Examples include epoxy and phenolic resins. Thermoplastic polymers soften when heated and can be reshaped. Examples include polyethylene and PVC. Wood. Natural wood is used in construction and furniture due to availability and ease of processing. Modified wood, such as plywood or laminated timber, improves strength and stability. Rubber. Natural rubber is derived from latex and valued for elasticity. Synthetic rubber, such as neoprene, offers improved resistance to heat, oil, and chemicals. Ceramics. Ceramics include materials like porcelain, glass, and alumina. They are hard, brittle, and resistant to high temperatures. Composites. Composites combine two or more materials to achieve superior properties. Examples include reinforced concrete, fiberglass, and carbon fiber composites. Module 1 Summary. In this module, we explored the fundamentals of material science, starting with atomic structure and bonding, then crystal structures and dislocations, and finally the classification of materials. These concepts are essential because the performance of engineering systems depends heavily on choosing the right material and understanding its microscopic behavior. In the next module, we will apply this understanding to engineering statics, exploring how forces, equilibrium, and structural analysis govern the performance of engineering systems.